Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. We will continue discussing some various facts from abstract algebra. In the last lecture we discussed about groups. In this lecture we will discuss about two other algebraic structures, namely rings and fields, which will be useful when we will design MPC protocols. So, what is a ring? So, remember when we discussed groups, in group the set G involved a single operation, namely the operation O. But when we consider a ring, we will be given a set R, and now there will be two operations instead of one operation. I could have called them as operation O1 and operation O2, but instead we use the notation plus and notation dot for the operations O1 and O2. Both of them will be binary operations, namely they will be operated on two elements at a time from the set R. And the important thing to note here is that this plus is just a notation, it is just a representation for your operation O1. I could have used operation O1, but instead I am using the plus notation here, and this is just a notation. This is not a regular addition operation. Okay, so you should not. So, whenever I write A plus B here, where A and B are elements of the set R, we should not interpret it as if I am going to add the elements A and B in the integer sense. Even though I will say that I am going to add A and B because I am using the notation plus here, but that is not the usual addition operation. The addition operation will be defined as per the set R. Okay. So, my addition operation plus operation could be here the addition modulo n operation. Even though it is addition modulo n operation, I will be saying, or I will be using the notation plus to denote that. So, that is just an abstract notation here. In the same way, this operation dot is an abstract notation for multiplication operation or the operation number 2, but that need not be always the integer multiplication or real number multiplication. It is just an abstract notation. Okay. So, for the groups we require that the set G along with the operation O should satisfy certain properties. Now, for R to be considered as a ring with respect to this plus and dot operation, some properties should be satisfied. So, let us see what are the properties. So, the first axiom, the first ring axiom is that if I consider the set R along with the plus operation, it should constitute an abelian group. Now, what is this abelian groups? It is a special type of group. So, since the operation plus should be should satisfy the group axioms, that means the closure property should be satisfied. That means you take any pair of elements A and B from the set R, add them, you should obtain back the element from the set R itself. The plus operation in your set R should be associative. There should be some special element 0 from the set R, which should be the additive identity element, and there should be an additive inverse element for every element A. So, up to this point we have just considered group axioms. Now, what is an abelian group? It is a special type of group where a fifth property is satisfied, namely the commutative property. So, remember when we discussed the properties of groups, there I stressed that it is not necessary that if your operation O is associative, it should be commutative. That may or may not be the case. So, that is why every group need not be an abelian group. It will be considered as an abelian group if the operation O, which in this specific case is the plus operation, is also a commutative, it also satisfies the commutative property. If it does not satisfy the commutative property, then it will be not considered as an abelian group. Okay. So, my first ring axiom is that if I perform the plus operation, again I stress by plus mean whatever way I define the plus operation, if I right now considering it as an abstract operation. So, the first ring axiom is that the plus operation over the set R should constitute an abelian group. That is the first requirement. The second requirement is that if I consider the dot operation over the set R, then it should also satisfy certain properties, namely it should satisfy the closure property. That is, if you take any pair of elements from the set R, perform the dot operation, you should get back an element of the set R. The dot operation should be associative over the set R, and the dot operation should have an identity element, namely there should exist some special element which I denote by 1, such that it constitutes an identity element for every element A from your set R. That is the second ring axiom. So, the element 0 here, I will call it additive identity if it exists, and again this is just a representation of some special element, namely the identity element, that need not be the integer 0. Okay. And the inverse of A with respect to the plus operation, it will be called as the additive inverse. Additive inverse of A. Again, this should not be interpreted as the negative A, it is just a representation of the element. The property of this minus A element is that if you perform the plus operation involving this element minus A and element A, you will get back the 0 element, which is the additive identity element. In the same way, this element 1, if it exists, need not be the integer 1. It is just a representation of a special element from your set R, and if such a special element exists, then I will call it as the multiplicative identity or the dot identity. That means, it constitutes the identity element with respect to your dot operation. The third property which the plus and the dot operations should satisfy over the set R is the following. It should satisfy the distributive laws. What are the distributive laws? The requirement here is that the dot should be distributive over plus in these two ways. Okay. If all these three properties are satisfied, R1, R2 and R3, then I will say that the set R along with this abstract plus operation and the abstract dot operation constitutes a ring. If any of these three properties is violated, then I will not be calling R as a ring. Okay. So, let us see some examples of rings. So, let us consider the set Zn, which we have defined in the last lecture. It is a set of all possible remainders which you can obtain by dividing any integer by a modulus n. And now I consider the addition modulo n operation and the multiplication modulo n operation. So, basically what I am saying here is now my abstract set R is Zn, my abstract plus operation is actually the addition modulo n operation which I have defined in the last lecture, and my abstract dot operation here is the multiplication modulo n operation which also I had defined in the last lecture. And now let us see whether all the ring axioms are satisfied or not. In the last lecture we already proved that Zn along with the operation of addition modulo n is a group. We already proved that in the last lecture. It satisfies your closure property, the operation of addition modulo n is associative, the integer element 0 which is a member of the set Zn is actually the additive identity element, and n minus a, if a is an element of Zn, then the element n minus a will be the additive inverse element, and that is why all the 4 group axioms are satisfied, but it satisfies the additional property that it's the addition modulo n operation is also commutative, because if you perform a addition b modulo n, the result will be same as b addition a modulo n, because both of them will give you the result a plus b modulo n. So, that is why your addition modulo n operation is commutative, and that is why the first ring axiom is satisfied. That means, with respect to the abstract plus operation, where the abstract plus operation in this case is the addition modulo n operation, the set Zn is an abelian group. Now, let us consider the multiplication modulo n operation and see whether it satisfies the closure, associative and identity properties. The closure property is guaranteed because you take any two numbers in the set Zn, multiply and then take modulo n, the result will be an element of the set Zn. The operation multiplication modulo n is associative, and the integer 1 which is belonging to Zn will be the multiplicative identity. That means, in this case indeed 1 is should be 1 is actually the integer 1, okay, multiplicative identity. Now, let us see whether the distributive properties are satisfied with respect to the addition modulo n and multiplication modulo n, and it is easy to verify that indeed the distributive laws are satisfied. Okay. So, I leave it as an exercise for you. You can easily prove that if you add b and c and then take modulo n and call that number as r, and then if you multiply a and an r and then take modulo n, the result will be same as if you first multiply a and b modulo n and then multiply a and c modulo n and then add the individual remainders and then take modulo n. The result will be the same, and same way you can prove the second distributive property as well. Okay. So, that shows that the set Zn along with the operation of addition modulo n and multiplication modulo n constitutes a ring. Now, this is a very interesting ring, because if I consider the moduluses of the form 2 power 32, 2 power 64, 2 power 128, 2 power 256, then basically this captures the special case of integer arithmetic performed inside your computers, because typically inside your computers you have registers which are typically of size 32 bits or 64 bits, well 128 bits, or even if you have a very powerful machine, then the registers will be of size 256 bits. They can store any integer of length n bits. And now, if you have a register where you have stored an integer a, another register which has stored the value b, and both of them are n bit registers, and then there is another register c which is also an n bit register, and this register stores basically the result of adding the values which are stored in the A register and B register, then basically since C register can also store an n bit number, that means if the result of if the result of addition of A and B cannot be stored in an n bit number, then basically you have to that means an overflow has occurred, that means you have to reduce that value C modulo n so that it can fit an n bit register itself. So, basically internally what computer is doing is it is actually doing an addition modulo n operation. Similarly, if you have a D register which is also an n bit register and where you want to store the result of product of the values stored in the A and B register, then again if the value of A and B, if the result of multiplying A and B crosses an n bit number, then you have to do a modulo n operation so that the result can be kind of truncated and stored as an n bit number. So, there you are actually performing a multiplication modulo n operation, right, and that is why depending upon the size of registers which are there inside your CPU, which are typically of the form some 2 power k, okay, this ring Zn with respect to the addition modulo n operation and multiplication modulo n operation actually constitutes or it mimics the integer arithmetic performed inside your computers, right. Now, let us introduce our third algebraic structure which are called as fields, and here also you have abstract plus operation and abstract dot operation as it was the case for rings, and now you demand some more you demand some additional axioms over the ring axioms. So, when we will say that the set F constitutes a field with respect to this abstract plus and abstract dot if the following conditions are satisfied. So, the first field axiom is that the set F along with the abstract plus operation should be an abelian group. Well, this was the requirement even for the case of ring. For the rings, whatever was the set, the plus operation with respect to that set should constitute an abelian group. Now, the second requirement here is that if I exclude the additive identity, which I often call as the 0 element, by a 0 element I mean the additive identity. That does not mean that a integer 0 is a member of F, no, remember 0 is just a representation. So, the demand here is the following: if I consider the non-zero elements from the set F, then with respect to the dot operation, that truncated set should also consider an abelian should also constitute an abelian group. Now, this is a new property, because if I go back to the requirements of ring, then in the second ring axiom there was no demand with respect to the dot operation, namely it was not required that the dot operation should constitute a group. We needed only the closure property, associative property and the existence of the identity element. It was not required in the ring axiom, second ring axiom, that the dot operation should also satisfy the group axioms. But now, when I come to the field, the demand here is that if I consider the non-zero elements of the set F, then along with the dot operation they should satisfy the requirements of abelian group. Okay. Namely, the closure property should be there, associative property should be satisfied, identity element should be there, and the inverse element also should be there. And of course, like we had the distributive law for the rings, we demand that the dot should be distributive over plus in the case of fields as well. So, if we closely compare rings with fields, what we can say is the following: a field is a special type of ring where every non-zero element is also invertible. That need not be the case just for a ring, because for a ring if I consider an element from the set R, that may or may not have a multiplicative inverse, but the axiom number F2 demands that every non-zero element is invertible and has a multiplicative inverse. So, that is why field is a special kind of more powerful algebraic structure compared to ring, because in ring, since the every element need not have a multiplicative inverse, you may not be able to do the division operation. What do I mean by division operation in a ring? So, if R plus and dot is a ring, then for A comma B belonging to R, A divided by B is interpreted as A multiplied with the multiplicative inverse of B. That is the interpretation of A divided by B in a ring, abstract ring. But at the first place, this element B inverse may not be present in the ring R, because a ring does not give you the guarantee that every element has its multiplicative inverse. But if I consider a field, then for any A comma B belonging to F, A over B is interpreted as A dot multiplicative inverse of B, and now because of this second field axiom, B inverse is guaranteed to exist, because B will be A B belonging to F minus the 0 element. Okay. So, if both A and B are non-zero elements, then A over B should be interpreted as A dot B inverse, and since B is a non-zero element because of this second field axiom, it will be guaranteed that B inverse exists. So, that is what is the interpretation of division operation over rings and fields. Okay. So, basically the idea is that you now are given the flexibility to do both multiplication, addition, subtraction as well as division. In rings you may or may not be always able to perform the division operation, because the multiplicative inverse need not exist, but over a field you can always perform division involving the non-zero elements. Okay. So, what could be an example of a field? The simplest example is the set ZP, where P is a prime number. So, for instance, if I consider the set Z5, because if I take P equal to 5, which is a prime number, then Z5 will be 0, 1, 2, 3 and 4. Then you can verify that field axiom 1 is satisfied, and if I take Z5 minus 0, then as per our definition of ZP star, this is Z5 star, because as soon as I exclude the element 0 from the set Z5, right, I get all the elements which are co-prime to 5. So, 0 cannot be co-prime to 5. So, I have excluded it. Now, I have Z5 star, and now you can check that every element in this set Z5 star will have its multiplicative inverse. Okay. And of course, with respect to the addition modulo P and multiplication modulo P, the distributive properties are satisfied. So, that is why this is a very nice example of a field. Of course, we can have other kinds of field as well. We encounter what we call as Galois field, which is typically of the form some prime raised to power k, but most popular one which we used for implementation purpose is Galois field of size 2 power k. What is this field? Basically, this is a field. Here your F is collection of all k bit numbers, where k is some parameter. So, if k is equal to 2 for example, or if k say for if k equal to 0, then your GF k equal to 1, then GF 2 power 1 will consist of all 1 bit numbers. If k equal to 2, then GF 2 power 2 will have the bit strings 0 0, 0 1, 1 0, 1 1 and so on. And the plus operation and the dot operation over this Galois field is not the usual plus operation or the dot operation. Okay. They are defined in a special way. So, when we will encounter Galois field, we will see the details what exactly are the plus operation and the dot operation, and they satisfy all these field axioms. So, that is another popular field which we use. Of course, there could be other kind of fields as well. You can define field where the elements are polynomials, and then your plus operation is defined to be addition of polynomials, multiplication operation is defined to be multiplication of polynomials and so on, right. So, that is a field. An interesting property of the field is the following, which we will encounter, which will be useful when we will design MPC protocols. So, if you have two elements x and y which belongs to this set F, and F is a field, and if the result of x dot y is the 0 element, namely the additive identity element, then it has to be the case that either x is equal to 0 or y equal to 0. When I say x equal to 0, by that I mean that it is either the case that either your x is the additive identity element or y is the additive identity element. So, you can quickly verify that this indeed is the case for the this statement is indeed true for the case when your field F is the set ZP, but this property in general holds for any field. How we can prove it? We can prove it by contrapositive. What do I mean by proof by contrapositive? So, by proof by contrapositive I mean the following. If you want to prove that if P implies Q is true, then if P implies Q is true, then negation Q implies negation P is also true. Okay. So, one way of proving P implies Q to be true is show that negation of Q implies negation of P is true. So, this is your Q part of the statement. So, the negation of this statement will be that x is not equal to 0 and this OR gets converted into AND. Okay. So, I want to show that if x is not equal to 0 and y is not equal to 0, then even the result of x dot y is not 0. How do I show that? If x is not 0 and y is not 0, that means they are the non-zero elements of the field F, then definitely their multiplicative inverse exists. Okay. Why the multiplicative inverse exists? Because of this field axiom number 2. Now, consider this element, namely the element y inverse dot x inverse. Because of the closure property, since the dot operation satisfies the closure property and y inverse and x inverse are non-zero element, the result of y inverse and x inverse will also be an element of F. That means y inverse, that means I can say that y inverse dot x inverse is an element of F minus 0 because of the closure property. However, this is a special element. If you see closely, then this element y inverse dot x inverse constitutes the multiplicative inverse of x dot y. Why that is the case? Because if you take y inverse dot x inverse, this will be a field element which is not 0, and then if you multiply it with the element x dot y, okay, and x dot y is also a non-zero element from the field, because as per our assumption x is not equal to 0 and y is not equal to 0, and hence x dot y is also and since they are non-zero elements and the dot operation satisfies the closure property, x dot y is also a non-zero element. But now what will be the result of performing the dot operation on these two elements? So, I can apply the associative property and then say that this is same as y inverse dot x inverse dot x dot y, but the result of x inverse dot x will be the multiplicative identity element, namely 1. So, this will be same as y inverse dot y, and since 1 is the multiplicative identity, it being multiplied with y will give you the element y itself. So, you will get y inverse dot y, and y inverse dot y will give you again the multiplicative identity element, namely 1. That means, indeed this element within the bracket constitutes the inverse of another element, and as per the field axiom F2, the inverse element exists only for non-zero elements. Okay. So, that shows your x dot y is not 0, right. So, that means in a field I can always say that if the dot of two elements, right, is the element 0, then definitely one of them has to be 0. But this property need not be true for a ring, you can verify that. I leave it as an exercise for you. This property need not be true for a ring, it is true only over a field. Okay. So, with that I conclude my discussion over the algebraic structures that we need for this course. Thank you.